This lesson is about transverse and longitudinal waves. We'll take a look at examples of each so that you'll know and be able to explain the difference, and we'll also spend some time looking at how a longitudinal wave can be graphed on a displacement distance graph, because that can be confusing at first. So let's look at some examples. First, this is the simulation that we looked at in the previous lesson, and here's the URL at the top. We see a source oscillating up and down, and it's setting all the particles in the string oscillating up and down as well. But if you watch a crest or a trough, you can see that the wave itself and the energy that it's carrying is propagating to the right out the window. So we have this perpendicular arrangement between the oscillation of the particles and the movement of the energy or the propagation of the wave. And this is characteristic of a transverse wave. So we call this a transverse wave, where we have this perpendicular orientation between the oscillation of the particles themselves and the direction that the wave is propagating. So a wave on a string is an example of a transverse wave, where we see the energy flowing in one direction and the particles of the medium vibrating perpendicular to it. So in our case, the energy was flowing out to the right and the particles of the medium were vibrating up and down, which is perpendicular. That's characteristic of a transverse wave. This simulation is from Physics. The URL is up here, and this shows very different kind of waves. Notice here that we can see these bunched up areas that are passing towards the right. Those are compressed areas called compressions, and we also see areas where the lines are more spaced out. Those are called rarefactions, and we can see those are each passing towards the right. So we have a disturbance that is moving from the left to the right, these compressed areas and these spread out areas. But if you focus on the red line, you can see that the red line is just moving backwards and forwards, left and right, and the same thing with the green line as well. So although we have a disturbance moving off to the right, the lines, which are actually just a bunch of particles joined together, are moving backwards and forwards, and in this case they're moving backwards and forwards parallel to the direction of the wave propagation. That's characteristic of a longitudinal wave. So these are longitudinal waves. Here's another example. This is another simulation from PhET. Here we see a loudspeaker and particles of air, and if you focus on the red particles, it's easier to see than with the white ones, you can see that they're just moving backwards and forwards, left and right. And if you look at this one, you'll see that it never moves off the screen. So the particles themselves are not making any forward progress. They're not moving to the right off the screen. But if I were to show you the waves that are underlying those, then you'll see that the waves themselves are moving to the right off the screen. Here I'll get rid of the particles for a moment so you just see the waves. The waves are clearly moving to the right off the screen, but the particles themselves, which are transmitting that disturbance, are just oscillating backwards and forwards. So again, here we have longitudinal waves where the direction of the oscillation, left and right if you look along the middle here, is parallel to the direction of wave propagation, which if you look at the middle is to the right. So for longitudinal waves, like sound waves in air, if the energy is flowing off to the right, that's the direction of the wave propagation, then the particles of the medium are also oscillating right and left. In other words, they are oscillating parallel to the direction of energy flow, of wave propagation. And here is a diagram from Hamper Higher Level Physics, and the next one's from the same textbook. And we see an example of a slinky where you are pushing the slinky in from the right. So this is another example of a longitudinal wave. It's a way of getting a wave on a spring to be longitudinal. Of course, if you shook this up and down, you could get a transverse wave on this spring too. What I wanted to point out on this diagram is how to find the wavelength of a longitudinal wave, which can sometimes feel confusing at first. You just go from one point in one compression to the same point in the next compression, or you could use the rarefaction as well. So here you see the center of one compression to the center of the next compression. That's one wavelength. Last, let's look at how to draw a displacement position or a snapshot graph of a longitudinal wave. We have a bit of an issue when we try and do that, because here we have the oscillations being backwards and forwards in the same direction as the position along, in this case, the spring, and here on the graph, our x-axis. So we don't have a good way of drawing this forward movement along this dimension. So what we do instead is we turn it sideways. So if you look at the spring here at rest with positions 1 through 13, then we see a compression over here and a rarefaction over here, but we take a look at where all the particles have gone. And this is illustrating that this particle has moved that way, this one's displaced to the right, displaced to the right, displaced to the right, displaced to the right. This one's not displaced, and then this one's displaced to the left. as are all of these. So, and then this one's not moved again. So this is particle 2, particle 3, particle 4, 5, 6, etc. So what we do is we just take this distance and we plot it vertically. So I'm going to take that distance there, and I'm going to go to the starting position where that particle was, and I'm going to plot that distance right there. For the next one, I go to the starting position where particle 3 was, and I plot that distance here vertically. So I'm still plotting the displacement that it is from its equilibrium position, but I've turned its horizontal displacement into a vertical graphing. So if the points are above the position axis here, this is displaced to the right, and if they're below, that means they're displaced to the left. Following through, you can see how that works. Now over here, if something is displaced to the left by that amount, I'm going over to its initial position, which was there, and I'm graphing that vertically. So again, below the line means to the left. So hopefully that helps make these make a little bit more sense. By taking this approach, you can draw a displacement position graph of a longitudinal wave that actually makes it look a lot like a transverse wave. So those are transverse and longitudinal waves.